class, and then we'll continue working on this stuff, okay? So, number 1 states, find the network of a piston cylinder device filled with air assuming an isothermal process if the pressure changes from 100 kPa to 350 kPa, while the initial volume is 0.5 meters cubed and the initial temperature is 100 K. So, when you're doing this problem, keywords are what? Isothermal means it's constant temperature, okay? What kind of fluid are we using? Air, and air is a ideal gas, okay? So we know we're using air, and we know we're using a constant temperature process, and what's happening? The initial volume is 0.5, and we know something happens to the volume, right? It either compresses or expands, right? So what type of work is that? Boundary work. It's boundary work. We don't know if it's negative or positive yet because we don't know which direction it's going, right? So we know it's boundary work. So what were you saying, Kevin?
The temperature doesn't change, so we know that if the temperature went up, the volume went down.
Let's see what happened. The pressure went up, so the volume has to go down, right? Yep. But if you didn't know that, then you could just wait to find the volume. All right, so problem 1. We're looking for boundary work. Where do we go to find that boundary work equation? What did I say? It's air, ideal gas, isothermal, and yeah, you could do this, right? We had one of those in our cheat sheets.
For isothermal?
For isothermal, yep. For air, for an ideal gas.
Did you remember the report?
I am, yes.
Okay.
Yep.
I didn't see it start.
Yep.
Why are they all down for forms as isobaric, isometric, and polytropic? Oh, I don't know.
You should have isothermal somewhere, unless you missed it.
CLN.
Yeah, but it's in your cheat sheet too. What is the equation I have as RT ln of V2 over V1? Right? If it's, yeah, you might have missed it in your notes, but it's in the cheat sheet too.
Oh, okay. Not we probably maybe we didn't do it this time.
So we have, where do we find our tables? Hopefully you kind of know that by what it is for air. What is it for air? Yeah, 0.287 kilojoules per kilogram K, right? And we know the temperature. Temperature is what, 100 K? And we know V1. So what are we missing? Yep. Now, in the cheat sheet, do I have formulas to find if you know the pressures? Did I do that somewhere for you? I did. There. So the page before in your cheat sheet, it's P1 over P2 equals V2 over V1. Is that what you have? Where does that come from? The ideal gas from state 1 to state 2, and assuming the temperatures are constant. Yep. And look, what can you do now? Yeah, you can just solve for V2. So that's P1 over P2 times V1. And you get 0.1429, which, based on Kevin's assumption, is correct, right? So you're going, you're compressing, right? So that work is negative, you'll get negative, or it's in, right? Not out. So in the end, you end up getting this. You could try this on your own time. But WB becomes negative 3.59 e to the plus 4 joules per kilogram. So the negative just indicates it's coming in, it's compressed. So on your sketch, if this was the first law, you draw an arrow in indicating WB. Yes?
You will use that, boundary work formula if it's isothermal, or you always use that.
So this right here that I boxed is the fundamental equation for boundary work. If you know it's isothermal in a gas, that is valid. Okay? Only for isothermal in an ideal gas. If it was nitrogen, same equation. What's different? R. That's it.
So boundary work is negative always, then it's going in.
It's compressing. It's in. It's work in. Yep. All right. Questions on this one? All right. The sketch? Oh, it just doesn't matter. You can have vertical or horizontal. So I'll label my boundary kind of at state 2. And it'd be something like that. All right. So let's review. And what we're going to have to do first is review this. Why? Why do we need to review these?
Is it one so great at?
Say that again?
Is it one so great at?
No, okay, sure. But these are very important when we start dealing with the first law, right?
Yeah.
Because why do we need to know where we are?
It tells you what state you're at.
It tells you what state you are, right? Because could be a liquid, could be a mixture, or it could be a gas. And it also tells you, if you look at the process, if this is a constant line on the T, what does that mean? Yeah. Constant temperature, isothermal. If it's a line straight up, constant volume, also called isometric. Isometric. What's this called? Isobaric. Yep. Okay. And what's the last one that I probably won't test you on, but we've had a homework on? Polytropic. Okay. And that one was PV to the N equals C. What's that?
Everything moves.
Everything moves. Hmm?
Yeah. In polytropic, temperature.
Oh yeah.
and
Yep.
pressure change.
Everything can change. Yep. Typically, that's what happens in real life. Yes.
You know how when it's under the vapor dome and the line goes straight, it's isothermal and isobaric? Or the pressure doesn't change?
If you go from here to here,
No, if you go from, sorry,
here,
left to right,
here.
the temperature stays the same, doesn't pressure also stay the same?
Yep. P and T is the same, but what happens to volume?
It changes.
It gets bigger. Yep.
So if a line just goes straight through, is pressure constant too?
Straight
You know
through.
how we did the isothermal?
Like you mean like this?
Yeah.
If it's in between the lines, then we would have constant pressure. Yep. 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 What do we need to know when we're inside here? The state 1. Yes, the quality. Yes. Try to remember that. It's quality, right? Say that again?
If you know the difference between the two temperatures and the temperature you are at, or sorry, yeah, no, two temperatures of saturation, you know what temperature you're at, and you figure out X
Not using the temperatures. You have to use
for the specific volume.
UF or UG or VF or VG, right?
Yeah.
Yeah, etc. Yes. Those are the equations that are in your cheat sheet. All right.
Like there was the one where it was like we were on saturated vapor line, and then it said that the volume reduced by half. So it's
Yep.
like by visualization, you can see the quality is different.
Yes. Yes. Yep. Yep. So always remember, if you're in the middle here, you need to know quality because you have to find your U values for that. Because where do the U values fit in? To the first law. Okay. I'll erase all this for right now. Draw more lines. What are those lines called? Yep, they're constant pressure lines on the T, and these are called constant temperature lines.
Why the opposite direction?
Just fundamental. Yep. I don't know. Ask whoever invented physics. I don't know. Just the way it works, I guess. Yeah, it could be that. Well, over here it's due to like the ideal gas equation and stuff, the trends. Yep. All right, questions on this? All right. So you could have questions regarding this in combination with the first law, right? Everything we've been doing builds upon this test. So make sure if you are still struggling with this stuff, you let me know today or tomorrow so I can help you. The first law is the biggest thing, right? And this is really what you need to do every time, right? It's a closed system. Am I going to do open system? No. It's only going to be closed. So it's only that.
So on the test, you don't need to see it just crossing out PE, KE, or.
Nope, don't worry about that. Don't. Yep. That is big U. It's always big U. Okay? Because you can rewrite this as what? Yep. And these could also be little q's, right?
Yeah.
Right? That's valid, right? What about the next one, where you could have U dots? Yeah, I have. Yeah.
Solve for
Yeah.
specific.
So then your answer would be per kilogram.
Yeah.
Yep. Yep. All right. So when you do these problems, always try to draw either that or the PV one, right? First step in the engineering problem. Do it. Yes.
Will you ever have a reason you want to go with
No, not really. Those are typically used for phase, like if you're looking at the triple point, okay? But typically, you're going to draw one of these, okay? Later on, we're going to draw where instead of V, it's S, okay? But we're not there yet, all right? For open system. So you have temperature, pressure versus this. Do that. Figure out where you are in the states, somewhere, all right? Second one. Say you have a cylinder or some system. Draw your system and draw your boundary and then label everything, right? Because you could have shaft, you could have boundary, you could have electric, you could have Q in. Oh, that's Q out. You could have Q in, right? The voltage problem is probably the best problem that if you know how to do that, that's and pretty well, feel comfortable, that's pretty much everything I can cover you on a test, right? Because it has everything in there. It had electric, it had shaft, and it had boundary work. But the boundary work was going out, right? And you could have solar coming in, you could have heat loss through the walls, okay? Always remember that on the right side of this equation is stuff going across the boundary. See my arrows? They're across. Delta U is your change in internal energy inside. All right? So delta U is in here. That's your system, changing energy. If it's a gas, an ideal gas, can someone tell me what delta U is? Do we have to look up the change in internal energies? No, there's a shortcut. What's the shortcut? mCV delta T. Right? Make sure you know this, because if it's air, or if it's nitrogen, or whatever, this is the shortcut. You don't have to do any tables. M is your mass, CV is your constant in the back of the book, and this is your change in temperature. Only for ideal gas.
That's big U, right?
That is big U. That's only if both of your points, all your points are over there on the right. If it's on the line, I would not do it. Okay? Because the equations aren't quite perfect like that. What do you have to do if you're on that right line? What value is the G's? They're all G, table values for G. Yep. I won't put a spring. You could also have spring, right? I'm not going to do spring. Okay? I won't do springs. Will's happy. All right? Just because that's enough, right? You've already had a spring problem, and we'll have many more for open systems. All right? But for now, we'll ignore springs. Now, biggest thing too to remember. See how I wrote this? Left equals the right. And what do I always harp to tell you to do after this? Cancel stuff or break everything down into its easier forms. Okay? Because then you can figure out what you need to find and what you already have. Okay? What's the ideal gas equation? PV equals MRT. And P equals rho RT. And PV equals RT. I won't have anything with moles. Okay? And these are all the gas constant, not the universal one. I could have you graph something. On a graph, what are you going to include? Title. Y label. X label with units. Right? Yeah.
What over rho equal to
I was going to get there. Yep. So just a note. I think I had something else in there, but maybe not. What's the unit on density? Yep. What's the unit of V? Yep. So if you have one or the other, can you find one? Yeah, it's just the inverse of either one. Okay? Where do you find these values? In the back of the book. So you can always automatically find the density. Okay? Just a reference. If electric typically is always in, shaft is always in, okay? Unless you have a turbine, then what's that? Out. What's that? That's an open system, but you can still have a shaft in here that's spinning the opposite way that a regular spinning would, right? You're extracting energy, but I won't cover that, okay? So if it's a shaft, there's energy in. If it's electric, energy in. Boundary, we know if it's plus, it's expanding. If it's negative, it's compressing. Q. Q, if you have a positive Q, that means it's in. If you have a negative Q, that means it's out. Okay? That makes sense? So you could have energy lost through the walls here, right? Q. You could have energy coming in right now from the sunlight. Okay? All right. And we're producing heat, yep. All right, you ready for number 2? Okay, try number 2. Vertical piston cylinder assembly containing a gas is placed on a hot plate. The piston initially rests on the stop, so the onset of heating, the gas pressure increases. At what pressure does the piston start rising? And the piston moves smoothly in a cylinder. Because what are we always assuming in these cases? There's no friction, right? But we know there is friction, and what does that produce? Heat, which would be Q out. See how all these are now hopefully kind of coming together? But tell me what pressure this thing will start moving. You haven't realized how important these questions are. How many times have you seen these questions? A lot, right? You got a test question on it. I had you redo it for test corrections, I think, maybe. So you got to do a free body diagram of the piston. Those three forces. Doesn't matter. Actually, it tells you 1 bar, but that's pretty close. I don't care if you use 101 or 100. Doesn't really matter.
Also, you don't have to label the entire thing as a boundary, just. you're only
No,
doing it
because
on the piston.
just looking at that pressure, so that's fine. So P equals W plus P atmosphere over A divided by A. Remember, forces are balanced, not pressure. Forces are balanced. And that's what I think I gave people credit that just gave me that. I didn't even care about the answer. I just wanted to reiterate this, that this is how you do these problems. I think we did one problem like this somewhere last week, maybe, with the stops. It went with some 250 to 300, and then it finally moved at isobark, or was it isothermal? I don't remember. Isobar? Yeah, it was isobar. Yep.
Does the pressure when change?
Yep.
What do you
Yep.
put the zero instead of MA?
You could have put MA. Yeah.
And what you're just saying that MA is equal
Yep.
to zero anyway?
Yep. Because we're assuming that the piston isn't moving. It's not accelerating. Yep. Questions? TV. We could do TV. Sure. So, I'm just kind of winging this. I'm going to draw some constant pressure lines, just to kind of give me an idea. Say it was all gas, and the pressure was here. What would happen if the pressure was lower initially? It would move, right? So the volume is constant, right? And then what would happen? And then boom, say it jumped to here, right? And then it would follow this line, right?
This is the TV for this problem.
Yep. So it was at a lower pressure than this, meaning it's not changing volume until it gets to this pressure, and now it's starting to move. But remember, these are constant pressure lines, so it follows this line.
But why is temperature going down?
Because it's constant pressure, the volume is getting bigger. What has to happen? What pressure staying the same? Right? What happens to the volume? It increases, right? Increases. So what happens to this?
Those are pressure lines, though.
This is constant pressure lines. The temperature
T goes down.
T,
B has to go down.
yeah. So this should go up. Hold on, let's look back at our other problem. What problem was that we had? Oh, yeah, what'd I draw there?
You drew pressure ones. You said that.
Yeah.
That's how I was confused.
Yeah. See? I drew these ones. Thank you. Yeah, I told you. Okay, fix that. Thank you. How come you didn't tell me before? There we go.
You said you were drawing.
Yeah.
Questioning my existence
Yeah.
for a second there.
Yeah. That's right, correct? I was thinking, yeah. And we were over here, right? And then up. So it would follow this. There we go. Thank you. That's what happens when I wing it. I told you that. That makes sense now, right?
Yeah.
Okay. Good. All right. Let's move on to the big one here. What's that? For this one? It was 50 kilograms. Yep. You want me to give you the answer?
50.2.
Yeah, let me find it right here. 150? Yeah. Is that what you got?
Right?
Okay. So you can try that at home.
Oh. Yeah.
Because atmospheric pressure is 101, right? All right, let's go back and do problem 3. Here, I can zoom out if you want to finish copying too. Whoa, that's too much. Guess that's where that works. Can everyone see 3? All right, so you have a piston cylinder contains 2 kilograms of water at 50 degrees, and it has 85% quality. The water is then condensed to the saturated liquid line. Determine the heat transfer and the work during the process. So first thing I want you to do is make your sketch. So just to give you an idea, where are these 2 processes?
Underneath the dome.
Yep, they go left. They're in the middle. Yep. So that's the first thing. And what's the pressure and temperature? Yep. And pressure's constant. What are those values? Saturated values, right? Yeah, because you're under the dome. Yep. So what type of process is this?
Isobaric.
Isobaric. And isothermal, right?
That's only conduit. There's still internal activity.
Yeah, there's still, yeah, because U changes, right? Yep, which is different under the dome. Yeah, good point. So does everyone understand that? Even though it's constant temperature, you got to be tricky. You got to be careful when you're under the dome, okay? Because the internal energies do change.
Are you gonna lose points for not showing the constant temperature or the temperature lines in there?
No.
Okay.
All right, so let's draw this.
As long as we show you the phase.
Yeah, as long as you give me the points. Yep. So I did a PV. So that's state 1 to 2. And here is our piston device. And it compresses, right? We have boundary. And we could have Q out.
You know, compressed it with some vapor to.
Yeah, the volume went smaller. Yep. Yes.
The TV diagram.
It would be exactly the same. Yep. But be very careful. You can't assume that delta U is 0 because under the dome, these internal energies change. Okay? I think that's why I wanted to do this, to show you that. Be careful with that.
I didn't tell them it was
I just guessed. I'm kind of thinking, okay, it's cooling because it has to go from the vapor to a liquid, so I'm pretty sure it's probably out, but if you didn't know, then it would be negative, right? Yep.
That wouldn't be an accurate statement, though. It's not cooling. Temperature.
Yes. So sometimes, did it say cooling? Some of the problems are worded that way, and it's kind of, it's
Just
not
as condensed.
quite cooling, yeah. Yep. Heat is being extracted out, but it's not cooling, yep. Yep.
Which is weird.
Yes, under the dome, under the dome is weird, right? Like we live in under the dome.
We all live under our government.
What's the quality at 2? Yeah. Meaning that it's all liquid, right? So I'm hoping by now you've had enough practice. These are really the 3 things you should be doing, right? And hopefully this sets everything else up for the problem. To be honest, I don't know. How much did you really think about the problem? You just figured out where the states were, right? And you wrote your givens. Because then, when you do the solution, we know it starts with this, right? And we can start canceling now. Q in, there's no Q in. And there's no work out. Not under the dome. That's the part that I want to point out.
We are in isothermal process.
We're in a constant temperature process, but what happens to the internal energies in this case? They change, okay? So be very, very careful on that. Okay? If you're over to the right, like a gas, then those isothermal, isobaric, those cases you can. So this, let's break this down. U2 minus UF. Can I do that for you? Because it's on the line. Oh, yeah, did I do that? Yeah, sorry. Yep. It's U2. I'll just do U2 minus U1. That's what happens when I try to get ahead of myself. And we'll do this one more time. But U2 was UF, right? So, in an engineering problem, you'd probably get 10 or 12 points for this. And getting down to here, because you broke it down and you want to solve for Q, right, would give you probably another 10 points. Because why are we solving for Q? What did I always tell you in this class? You're either going to be given or you're going to solve for it. So we know we have to find what? Those 3 values? M is given, right? Yep. So we're going to find Wn. We've defined it as N. Okay. So the equation we get, do we end up getting, we'll end up getting a negative value in our equation. That means we assign it as N. That's correct. Yep. So, boundary work. What's happening? What's happening to the system? It's compressing at a constant pressure. Okay? So, if you're always stuck, we know what's boundary work is this, right? We take the integral out, you actually get this, which is the same as that. Is everyone agreeing with that? Do we have M? We have P?
No.
And this is actually what? V2 minus V1? So I'm going to give you these values, and you can try these at home. You get 10.23 meters cubed per kilogram for V1, and V2 should be VF, which is 0.001 meters cubed per kilogram.
V1 seems pretty high.
Yeah, you're almost, you're a lot of vapor, right? So what happens when some vapor, it actually expands more.
That much is huge.
Yeah, it's quite big, right? And WN, do we know the pressure? Yep, yep. So let me, P is equal to P sat at 50 degrees. And that value is 12.35 kilopascals. I hope you noticed how much stuff you do now is everything we've done before, right? And then finally the work in, you get negative 253. Meaning that it's work in, that's why we get the negative. All right, and on this side, V1, wait, I already did V1. U1 is 2.107 e to the plus 3 kilojoules per kilogram. And U2 equals UF equals 209.33 kilojoules per kilogram. And Q out becomes, and I'm getting 4049 kilojoules, but positive, sorry. Just want to make sure that made sense. 253. Did we arrange that right? 4049? 3,900. I brought that over. Let's do that one. I know WN is right. 253,000, right? $2,107,000.
What'd you get? What'd you get?
4049? Positive or negative? Positive?
Why did you make the 209?
Because it's kilojoules.
Wouldn't you
Yeah,
check
but
change
everything is
kilograms
in
too?
kilojoules.
Yeah, everything needs to be in kilojoules, and then
It was, and it's also
So
killed.
you made it megajoules.
we have to multiply. I multiply it by 1,000 to get into joules.
Why you have to change the joules, everything is in joules.
Yeah. Well,
And you also have
Because
killed.
you
yeah,
left-
everything.
left
If
it-
everything was in kilojoules, then it should still come out. Should. Hold on, real quick. So you.
you have you added, is this negative 253?
Don't include the negative row because it's work.
Yeah.
Show that.
Yep. So you get 4049. Yes. The negative from the work just indicates.
The signs are independent.
Yes.
They're kind of-
The reason this is technically just basic work, right? But remember, we had a homework problem. If this is negative, that we have, it's actually in. Yep. Okay, so be careful with the sign.
Yeah, that's what I
It was
did.
on the diagram.
That's what I was actually thinking too. So.
Yes, because we've assigned it as in. Yes, if we found that this work is negative, that means it's in. We've already assigned it as in, so we're good. Yep.
Doesn't that mean the incremental rate is the negative sign?
Well, when you put it back into your first law, we've already defined it as in. So you would take it out. You take the negative out. 40/40, that's fine. Okay? All right, if you have questions, let me know. All right? I'll post this for everyone.